All right, we're going to go ahead and get started here. Hello, everyone, and welcome. Thank you for choosing to spend your valuable time with us. Today's webinar will cover learning to bring TLS to any transport via wolfSSL IO callbacks, presented by engineer Anthony Hugh. My name is Emma, and I will be moderating the webinar. All attendees will be in listen-only mode. If you have questions, please use the Q&A box. After the presentation, Anthony will answer your questions. As always, our webinars are recorded and made available on our YouTube channel. If you'd like to stay updated with all the latest from wolfSSL, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Feel free to contact us via email at facts@wolfssl.com if you have any further questions. Before we dive into the technical presentation, I'd like to provide a brief overview of wolfSSL. Today, wolfSSL secures over 5 billion connections. We have more than 2,700 OEM customers and dozens of resellers. wolfSSL consists of over 50 dedicated employees, primarily engineers. This progress is of course supported by a strong partner network that we are very proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO 178 support, a FIPS 140-3 certification and a FIPS Ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfboot, Java wrappers and JSSC support, and commercial support for curl, and our newest product offering, wolfHSM. These offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. Now, I'd like to turn it over to Anthony to discuss learning to bring TLS to any transport via wolfSSL's IO callbacks.
Thank you, Emma. That was a great introduction. So my name is Anthony Hu. As a brief kind of introduction, I'm going to let you know that I've been working at wolfSSL for about 4 years now, and I have about 25 years of experience in the consumer electronics industry. I am talking to you here from Waterloo, Ontario, Canada. Okay, so let's get into the agenda for this talk. It wouldn't be an Anthony webinar without starting off with the motivation. Then we'll talk about a brief introduction to our IO callbacks API. We'll look at various examples. So we're going to be looking at first of all the trivial examples. Then we're going to be looking at language ports, transport specific examples, platform-specific ports, and a featured use case, which is Bluetooth over low energy, or BTLE. At the end of that, we'll do a Q&A. So what is the motivation for these IO callbacks? These IO callbacks have been in wolfSSL for a very, very long time. And if you know anything about wolfSSL, you know that we're very, very customer oriented. These are here because our customers need them. Why do they need them? Well, they might want to use TLS or DTLS over custom protocols or custom protocol implementations. So when I say protocols and protocol implementations, I'm talking about like instead of normally you would think of TLS going over TCP IP, but it doesn't have to do that. It could go over, just a wire. So it could go over UART, and we're going to be talking about that later. When I say protocol implementations, normally we think of having it go over POSIX, right? Like, so you just open a socket and you do a read and a write, and you open a socket and you do read and write, so on the socket. But you might not have a POSIX interface for your network interface. So, this good examples of this are just about any microcontroller. Microcontrollers with bare metal have their own UI, sorry, not UI, their own APIs for, vendor-specific APIs for accessing the networking hardware. So you might need to have custom IO callbacks for that. Different transports. So what do I mean by transports? This is kind of a loaded term. When I say transports, I mean like different hardware. So basically, I shouldn't have said UART when I said protocols. I meant transport. So platforms. What different platforms are we talking about? Again, I mentioned microcontrollers earlier. Um, you might be running on Zephyr. Zephyr has different APIs for accessing the network. You might be using LWIP, lightweight IP, in which case you're going to be using different APIs that are not typically there for sockets. And you might be doing testing and debugging. So one really interesting use case for these custom IO callbacks is using using them to do fuzz testing. So if you're doing fuzz testing, then you don't have a standards compliant client to talk to your server or a standards compliant server to talk to your client. So you're going to need these IO callbacks to do kind of tricky things. Okay, let's have an introduction to these APIs. So the APIs are very, very simple. We define these callbacks as having an SSL pointer. Sorry, these are callback functions that are type deft, and they're pointers to functions. The functions have parameters, of course, and they're going to have SSL parameters. They're going to have a pointer to a buffer, a size of the buffer, and an optional context. When I say optional, that could be null or not even set. So it doesn't really, depending on your specific situation, they might not, you might not even be using the context. And we'll get into that a bit later. So, yeah, so in both cases for send and receive, there is a buffer and a size, and you are either to pull from that buffer or fill that buffer. Um, so if you look at the second set of, sorry, that's the first two lines right there that I was specifying. The second set of lines here set the IO send and receive callbacks. And this is not very different from the next two lines here. The first two lines set it as a context, so that's when you have a wolfSSL context. But you can also set them once you've created the wolfSSL struct with using the wolfSSL underscore new API. And finally, if you are using the context, you can set the context via these final two APIs. Um, So one point that I should make is the send is always simpler than receive, or it can be just as simple depending on what you're using under the hood, but usually send is very simple. And the reason why is wolfSSL will, generate the buffer, and all you have to do is transmit it over the wire. Sorry, transmit it over whatever medium you're transmitting it over. So you're basically going to get a buffer and a size, and you send that buffer over whatever transport or whatever API you're using. It could get a little complicated if you have to send it, if you have to kind of make it into smaller packets or something like that. But generally speaking, you don't usually do that. You just send the whole buffer over the wire. Receive can get a little bit complicated because depending on the API that you're using underneath in your callback, you might have to buffer. So for example, the first time that your callback gets called, wolfSSL is just trying to figure out the size of the client hello message. So instead of, giving you a huge buffer for you to fill, it's actually going to only ask for 5 bytes. So if your system is not equipped to help you buffer your first packet or your first message, because your first message is likely going to be the entire client hello, but wolfSSL is only going to be querying for the first 5 bytes. So then you might have to buffer if your system won't buffer for you. So that's something to consider. And we'll be seeing examples of that shortly. Okay, so let's look at the trivial examples. So, like I said earlier, send is always simple, right? When we look at our TLS benchmarking app, that's actually part of wolfSSL. You get let's go back to the introduction. Another point that I have to make here is that these slides will show a lot of code. And the code is not necessarily what you're seeing in our applications. The code that you're seeing in this presentation is generally all has been simplified a little bit. Code for like error checking has been removed. Certain debugging output has been removed, and that's just for the clarity of the presentation. Also, each slide in here will have GitHub references, and those GitHub references will be fairly long. So if you want a copy of these slides so that you can copy and paste those references, you can email us at fax@wolfSSL.com to get a copy of these slides. Okay, so as I was saying, GitHub references to the source code are at the bottom. Note that there are no line numbers because obviously we're constantly developing this code, and those line numbers change. Okay, so in our TLS benchmarking application, in order to not bring in irrelevant timings such as network and operating system buffering time, we use a very simple socket interface for memory and socket interfaces for doing benchmarks. So in our client send, if you're using a local memory kind of benchmarking setup, we call client mem send, and we'll look at that in a moment. But if you're doing DTLS, then we basically just call POSIX send to. And then if you're not using DTLS, so you're using regular TLS, then we use regular POSIX send. The distinction between send to and send is a send to is over UDP, whereas send is over TCP IP. And DTLS obviously runs over UDP, and TLS obviously runs over TCP IP, so that's why they're appropriate. As I was saying, there's also at the very top use local mem and a client mem send, and that looks like this. So what's going on here? Basically, we're writing into a memory buffer, right? And the memory buffer is larger than the buffer that we have, and it might have unconsumed data. So we kind of have to increment certain pointers, certain index. We have to increment the index. So we have to copy into the buffer, first of all, at the current index. Then we have to increment the index, and then we have to increment the amount of bytes that are recorded in there. Yeah, and the info T is, of course, the context here that is passed in before. So that's the send buffer. That's the send callback. Now, on the same TLS benchmarking app, there is a receive. So the client receive is relatively straightforward. It's either using a memreceive, which we'll get into in a moment, or similarly to the send callback, we do a receive from. If it's a socket, then, sorry, if we're doing DTLS, we're going to be doing it over receive from. And if it's regular TLS, then we're doing a socket receive. Socket receive just basically calls POSIX receive. And again, this is appropriate because TLS is running over TCP IP, whereas DTLS is running over UDP. And so client mem receive is a little bit more oh no, it's just about as complicated as client mem send, right? So it's incrementing the bytes that it read, and it's doing a mem copy into its the buffer that was passed in. Yeah, and then it tells this in the info, it says that it's done, and then we're good to go. So if you look at the following references in wolfSSL as well as wolfSSL examples, you'll see that we use this IO callback in all of these examples and sample code. And you can go in, and what you would do is you would search for these APIs to see how they're used, and then either wolfSSL send IO send, or sorry, set IO send or set IO receive. And then the parameter here, whatever the second parameter was, you'd search for that, and that would be the callback. And you can use those as examples. Now, these examples basically all are cut down versions of this and this. What I mean by cut down is it doesn't bother doing one of these three. Sorry, it doesn't bother checking for all of these three. It basically it's basically set up such that it's doing one of those three options. So it's either doing a memory copy, or it's doing DTLS over over UDP, or TLS over TCP IP. Okay, let's look at some language ports. We're looking at send, right? So we're looking at our C# language wrapper that's included as part of wolfSSL. And as you can see, you can create C# callbacks and register them with these APIs. Same thing goes for our send C# send callbacks over in wolfSSL. You can use these these APIs to register callbacks. And these callbacks would be defined in C#, which is really interesting if you really think about it. It means you don't need to write C functions as callbacks. You can just write them as C# APIs, which gives you the richness and simplicity that C# supplies. Okay, so let's look at transport-specific examples. We're going to be looking at some work that I had personally done on STM32. Well, the transport that we'll be using is UART, and when you do UART over STM, when you do UART communication over STM32, you have to do the setup in the kind of STM32 cube IDE kind of what is it called? IOC configuration system. And so when you're doing that, basically you have to turn on UART2, and then that means that you'll be using PA2 or PA3. That can be changed, and those are pinouts. So if you look at an STM32 board, like an actual like Nucleo board, they've got like literally almost probably over 100 pinouts, and you can change those. but by default they're PA2 and PA3, and you can see that on the board they actually print UART and print TX and RX there. So by that's where their default set. And so in this case on the particular board that I have, which is an STM32 U575ZI-Q, um we're gonna the USART2 is available for these operations. And so we enable that under connectivity, and then we go to so yeah, for this particular platform, the STM32 U5, they have what's called GPDMA, so general purpose DMA. And what you do is you have to kind of set it up a little bit differently than previous platforms. And this, we're just going to go into how to set it up. And that's basically setting up the channels to map to different USART1RX and USART2RX. USART1 is for the debug output that goes to a terminal. So we would normally hook up something like PuTTY and hook that up to the USB on the PC so that we can get debug input. Of course, USART2, RX, and TX are for the actual TLS to go over UART, serial UART. And we have that set up so that it goes over an FTDI that's hooked up to USB on our PC. And we set up channel 1. We make sure that its request is USART1RX. Same thing with channel 2 with USART1TX. This one is special because we have to, of course, set up channel 3 as USART2RX, but since it's receiving, we actually have to set destination address incrementing to enabled. And what that means is that when the destination gets data, there's an index that's incremented, and that will let you know how much data is come in. This is very, very, very important because if you don't set this, and trust me, I've made the mistake of not setting this, then you can't figure out how much data has come in. And that's important because you need to know how much data, how big the data is so that you can copy it into your buffer. So for channel 4, it's just a regular transmit. So that's USART2TX. Okay, so here are the callbacks. This is really important for receive. So receive is the hard one. So let's look at what's going on here. So the first thing you have to do is create a static variable that specifies the message length and set it to 0 in the beginning. Then you have this what's called RX event callback. That's actually predefined by the STM32 what is it called? SDK. This is a predefined function that you can then override. So if you have it declared and defined, then you're overriding their default. And all we're doing here is writing the size of the packet into message length. This callback is being called because we're down below, as you can see, we're using the receive to idle underscore DMA API. And what's going on here in the UART IO receive callback is that we're getting a context here. Ah, shoot, that's not what I wanted. We're getting a context, and the context holds kind of a bunch of buffers, and we're looking and seeing, hey, in a previous call to this callback, did we get too much data? And if we did get too much data, is that extra data enough to satisfy this request? If it is, then we'll simply copy that data into the buffer and we'll increment the index. And then we'll return how much data we got. But of course, if it's not enough data, then we're going to have to read off the what shall we call it? We're gonna have to read off the line, off the UART line. And so what we're gonna do is we're gonna reset the entire context, or what we call the TB, the TLS13 underscore buff struct. And we're going to call how you are received to idle. Max record size is how big we're willing to take in, and that's been predefined, so the buffer is that big. And in this case, TLS underscore UART has been is a macro defined that has been defined to STM's UART2 pointer. And we check the status of this call. If Oh, this should be in a loop. Whoops. So there should be a loop around here. I made a mistake. I edited I edited too much code. This status and then check of the status is in a loop, and it should be in a loop, and oh, no, it is in a loop. That's right. Here we go. If the status is not how okay, then we go into a loop where we wait for message length to not be 0. Once message length, oh, sorry, if status is not okay, then we're going to return that there was a problem here. That's what this message says. And what that message says, wolfSSL cbio error want read, is to tell the system, hey, try again. Try and call this callback again. But if it is how okay, then we'll go into a loop that says that while message length is still 0, wait for 10 milliseconds. And then we keep on checking if message length is 0. So message length will change to something else if this callback is called, right? So once that callback is called, the message length changes to something other than 0, and then we copy that into this buffer. So for transmission, it's very simple. wolfSSL will give you a buffer and a size, and you'll just send it over via the how underscore UART underscore transmit function. In this case, FFFF is the timeout length, which is the maximum it can possibly be. And so we basically just wait forever until we get the data. In this case, if you've made a mistake and you got here by accident, you have to reset the board. All right, so some platform-specific examples. So for Renaissance, so the platform-specific examples are really, really simple. Usually because the underlying platform has done a good job in making things easy. So Renaissance has this r underscore t4 underscore I tcp/ip dot h header file, and that specifies these APIs here that we're using for receive and send. And these functions appear in just about all the examples that we have for Renaissance. And so you can see in these particular directories within wolfSSL how these APIs are used for these functions. For Arduino, there's an Ethernet send API. So I think you have to enable Ethernet within Arduino to be able to use this. But it's super simple. It's client.write for sending. And then for receiving, you just have to make sure it's available. It's actually available, and then you do client.read to read into the buffer, and that's about it. For PyPico is interesting because it uses, as I mentioned earlier, the LWIP API or lightweight IP. And the setup is really nice and easy. You call socket and you assign sock to socket, whatever socket returns. And we have the callbacks here that are being registered. And notably, we're using the sock as a context for the callbacks. And here are the callbacks. Sock is, as I said, we were setting sock as the context. So we get sock back as the context. And then we simply call the receive API with the sock. And for sending, it's just as simple. We get the sock from the context and we call send, and then we return whatever send returned. Okay, so Toppers. Toppers is a real-time operating system. I think it's popular in Japan, and we do I/O callbacks for that as well. This one's a little bit more complicated. Actually, it's just as complicated as it's just as simple as the other ones. I just decided to leave some debugging output and some parameter checks in here. So if context is null, then we're not getting what we need. And so then we return wolfSSL CBIO error general. But if it's not null, then we grab this, we set the CEP ID to the context, and we just do the send of the data. Note TMO underscore forever here, so FEVR. That just specifies that the timeout is forever, so there is no timeout. So again, if you get here by accident, you just have to reset the board. For receive, it's just as simple. So it appears that this one's going to be buffer. This API will buffer for us. So we'll ask for data, and we'll get the data. And if too much data comes over the wire, then the RTOS will buffer it for us. Okay, so here we are at the featured use case, which is BTLE, also known as Bluetooth over Bluetooth low energy. I forgot that. And really, this is you'll understand what I mean here when I say when I say that these IO callbacks are super general, because in all honesty, Bluetooth low energy, it has its own API on just about every platform that supports it. So we don't actually so if you look here down at the GitHub reference here, it's actually pointing to our Bluetooth low energy simulator. And what that is kind of just shows you how it all works. In your setup, you're going to have your own APIs. But in this case, what we're doing is we have a simulator, and the simulator runs on Linux, or any other POSIX system. And most POSIX systems have a FIFO implementation within their file systems. So basically what we do is we do Bluetooth LE simulated, Bluetooth low energy simulated in a file system FIFO. And so we use MK FIFO and BTLE C2S FIFO is basically a macro that's been defined, a variable, sorry, a static string that has been defined as a file system placeholder name. And so what's going on here is we make a FIFO two FIFOs in the file system. Now you can see that they differ in their names in that one says C2S and the other says S2C. So C2S stands for client to server, and the other one stands for server to client, right? And so this particular API is called by both the server and the client. And so if you're the server, you're going to open a read-only connection to the client to server. And if you're the server, you're going to open a write-only file descriptor to the server to client. Conversely, if you're the client down below, you're going to open a read-only file descriptor to the server to client FIFO, and you're going to open a write-only file descriptor to the client to server FIFO. So the send is very simple. You're going to check for the right Bluetooth BTLE version, which in this case is hard-coded to 1. And you're going to check for the type. You're going to make sure that the type is actually TLS. And you're going to grab the length. You're going to set the length. And you're going to send that over via BTLE send block. So BTLE underscore send underscore block is just basically POSIX write, right? So you're using write to send this over the FIFOs. FIFO, by the way, stands for first in, first out. So receive is just a little bit more complicated. You're gonna check the blocks for the right versions and set the length to the receive, set the receive position. Oh, I'm going backwards. You're gonna so the first thing we do is we mem set everything to 0, and then so we're initializing the whole struct to 0, and then we're doing a BTLE receive block, which is basically just POSIX read. Little typo there. Sorry, that shouldn't say POSIX write. It should say POSIX read. And you're going to read into there, and then you're going to again set the Bluetooth version, and you're going to set the total, and you're going to set the position to 0. And so that's for later, so that in a higher level of the callback, they can check to see if well, we're doing buffering here in case we've read too much data, more data than the actual wolfSSL needs. And so yeah, this continues the receive function, and if there's like a problem, if for example if rec is less than 0, we basically zero out the entire structure and say, hey, something bad happened. And there it is. There I actually wrote it correctly. BTLE underscore receive underscore block is basically just POSIX read. And that concludes our presentation. So we are at the end. Emma, can you let me know if there's any questions for me?
Yes, there are a few. Thank you, Anthony, for that great presentation. Jumping into the questions, from the signature of the custom receive callback, it looks like we are kind of forced to do a mem copy into the buffer that is likely internal to wolfSSL. Could we instead just provide a pointer to an existing data buffer to wolfSSL? That way it would save the mem copy.
Interesting. In theory, I don't see why not. However, I don't know that we in wolfSSL if we did that. So obviously the API, no API, the not obviously. Sorry, I'm thinking as I go here. We don't provide such an API to just let you give us the pointer. But I think we, based on the structure and the code of wolfSSL, we might need a buffer anyway. So what would probably end up happening is we would copy your buffer, the contents of your buffer into our buffer. So we would basically we would need such a buffer anyways. So I think the point would be moot. That said, um, I it might be a possibility. So let me explain the reason why I think we would still copy it into our buffer anyway. And the reasoning goes like this. We When you're doing TLS 1.3 with something like X25519, X4, or sorry, ED25519, or let me think here, or ED448, we might not, you might need the entire TLS transcript because we're not hashing the handshake transcript. So we have to buffer the whole thing because that particular signature algorithm does not operate on a hash. It operates on the entire message. But that said, that's not true if you're using ECDSA or RSA for authentication. So maybe we wouldn't have to have our own buffer. That's a really interesting question. Whoever asked that, can you send that as a feature request to fax@wolfSSL.com, and we can further discuss it. I'm thinking on my feet here, and you've caught me off guard. So I think it would be really great to kind of have a conversation about that particular idea. And if you could send the proposal to fax@wolfSSL.com, or even support@wolfSSL.com, we can get started on that conversation. Thank you very, very much. It's a definite possibility, I think. Oh, and especially with the upcoming post-quantum algorithms, they also sign messages, not hashes. So yeah, let's talk about that. Please do send a message to fax@wolfSSL.com.
Wonderful. Moving on, I noticed you talked about TLS over UART. Can you do it over SPI?
Yeah, yeah, of course. So this presentation is slated for 1 hour. We could go over all the, what is it called? All the transports. You can do it over SPI. You could do it over I2C, sorry, I squared C. You could do it over, and it's not just STM32. You could do it, on microchip. You could do it on a plethora of NXP microcontrollers. They all have their own APIs. So I didn't go into how you would do it for all of them. But yeah, you can, as long as when you receive, you can figure out how much you received, then you can do it. So for example, I had to use a special API, um, read to idle. Sorry, what was I'm gonna go back in my slides here. So in the receive, we used how underscore UART EX underscore receive to idle. And that receive to idle let us get a callback, which was the RX event callback. And that specifically told us the size. So as long as your transport and API for that transport allows you to receive a buffer, and that buffer has a size, specifies a size, then you are good to go. You can use it on any transport you want. So like I said, SPI, I2C, I squared C, anything, even over CAN bus. We can do this over CAN bus without any issue at all. Thanks for that excellent question.
Wonderful. Well, I think that's the end of the questions. Thank you, Anthony, for hosting an informative webinar. Thank you to everyone for joining. I will email a copy of the webinar recording. You can keep up with our upcoming events, meet our team in person, read our blog posts, and get the latest wolfSSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any questions, please reach out to us at facts@wolfssl.com. Thank you again, and we look forward to seeing you on July 23rd for our automotive webinar. Thank you all.